Hello everyone, welcome back to PTech Chemistry channel. My name is Dr. Ant. In this tutorial video, we'll go through this Cambridge International IGCSE Chemistry Extended. This is for the 0620 Paper 2 Variant 1. So 45 minutes, 40 questions, multiple choice, pretty direct. However, there are some confusing questions, something to confuse the students obviously. This is for the October-November 2022 series paper. In this first question, we're looking at changes of state. So we're looking at energy being given out, energy being released to the surrounding is something we learn as exothermic reactions. But this is about changes in the states of matter. So going from solid to liquid to gas, we know that these are high speed. So the particles move at high speed in the gaseous state, whereas they only vibrate at very low speed in their fixed position. So in terms of kinetic energy, you go from low speed to high speed. So these are low energy going to high energy particles, going from the left to the right hand side, going from solid to liquid. And therefore, we're looking at energy being given out. So that means we are looking at going the opposite way, because that is going to lose energy as you go from high energy to low energy. We are losing heat energy. So there has to be gas going to liquid, liquid going to solid. So we're looking at 3, we're looking at 4. So answer must be D there. Question 2. We know about chromatography is used to separate colored dyes. So one of these components of the dye has an RF value of 0.86. When we have a chromatogram, so say this is our solvent level, so we know that our baseline, so this is our baseline where we are going to put the spot of our mixture on, must be above the solvent level, so that your substance, your mixture, will not actually dissolve in the solvent, but as the solvent slowly goes up, it's going to bring along the soluble solute, and then you will take it out before it reaches all the way to the solvent front. So how much the distance of the solute actually travel is going to be divided by the distance from the baseline all the way to the solvent front, okay, because baseline was the starting point. So perhaps I can just move my baseline a little bit closer to the bottom, and there's the solvent front there. So if we have that, we're looking at 13 cm divided by something equal to 0.86. So what distance did the solvent front move? So basically 13 cm divided by x cm is equal to 0.86. That's the RF value. So x is going to be 13 divided by 0.86. Straight away division on your calculator, we get x equal to 15.1 cm. This is to 3 significant figures there. Question 3. We have a mixture that consisted of salt, sugar, salt, sand, and sulfur. So salt dissolved in water but not in xylene. And then sulfur dissolved in xylene but not in water. Sand does not dissolve in water or xylene. So what is the order process used to separate all of these? So the first thing you should probably do is to dissolve, let's see. So I guess if I have in water, in xylene, so salt dissolved in water but not in xylene, sulfur dissolved in xylene but not water, but sand does not dissolve in any of them. So I think it doesn't matter whichever one you add first, but you're going to be able to separate the sand because sand will be insoluble, I think. Let's see. So if I add water first and then I filter, I'm going to get rid of the salt because both of these are insoluble in water. So I think adding water and filter, this one will get rid of salt, which is soluble in water. And then in your solution, you are going to get these two, which are insoluble. And then to the filtrate, so these two are insoluble, so it will be to the residue. You add xylene, and then xylene will be able to dissolve the sulfur but not the sand, so that one should be okay in xylene because we're adding it to the residue there from the first filtration. These are the residue from the first filtration. So I think this is a good question actually. This is your first filtration, and hence that should be dissolved further in the xylene to the residue, and then you'll be able to filter to remove the insoluble sand, but then the soluble stuff. So having said that, I think A is definitely wrong. Having said that, if I add xylene first, if I add this one xylene first, then I'll be able to get salt and sand in the residue. And then when I add xylene again, that's not going to be helpful because I'm adding xylene 2 times. So D is definitely a wrong answer. How about C here? When I add xylene first, these two are insoluble, salt and sand. When I add water to the filtrate will be not useful, because what you want is you want to add water to the residue so that you can dissolve the salt in water, but not the sand. But here it's adding to the filtrate, which is the soluble xylene, and that's not useful there. And that's why B must be the best possible answer. Playing around with words there, to be honest. Question 4, we're looking at isotopes. These are of the same elements. Number 1, they're atoms, same chemical properties. We do know there is property of isotopes because they have same number of electrons in the outer shell. This is as stated in your syllabus, which you can find out from the syllabus booklet. They have the same number of electrons and neutrons. That one is wrong. Should be the protons, but they have different number of neutrons there. So 2 is definitely wrong already. So that means A must be wrong. C must be wrong. 1 is definitely correct. So therefore, B must be the answer because there's no number 1 in D there, which means D must also be correct based on this B being the only combination that's correct. Same number of electrons and protons, as we said, different number of neutrons there. Question 5, what type of structure and bonding is present in an element? We're looking at malleable. Malleable, so that is a property of metal as your layers of cations of the same sizes. As we draw out the giant metallic structure, these are layers of cations in a sea of delocalized outer shell electrons. So we should be able to label, these are your sea of your valence electrons that get delocalized, so no longer inside the shell. These are your layers of cations of the same sizes that can slide past each other. When you apply force onto it, that's the property called malleable. And you can conduct electricity in the solid state. There's metallic structure there. So we're looking at giant metallic lattice, D there. Number 6, potassium bromide. So we know this is between a metal, a group 1 metal, and you have a group 7 non-metal. So we have an ionic compound. So this is a K plus, courtesy of the group 1 metal having lost one of the shell electrons. We have Br minus as a result of the group 7 non-metal gaining 1 electrons that the potassium atom has lost. And the overall compound there, we know that it will dissolve in water. So all potassium salts are soluble in water. That is part of the solubility rule in salt preparation topic. Conduct electricity when solid, not through electrolysis. When you are molten ionic compound or when you are dissolved in water, only then ionic compound can conduct. High melting point, strong ionic bond between the oppositely charged ion. Only 1 and 2 are correct there. Question 7, we're looking at similar structure to silicon 4 oxide. This is your giant covalent lattice structure. So in the giant covalent lattice structure, we have each silicon is bonded to 4 other oxygen, and then each oxygen having formed 1 covalent bond, each oxygen is bonded to 2 silicon atom, as you could see there, and then each silicon in turn is bonded to 3 other oxygen. So altogether that each silicon forms 4 covalent bonds there. So as a result of all that, which one looks similar? We're looking at similar structure, so giant covalent. So definitely not carbon dioxide. Carbon dioxide is simple covalent. Definitely not sodium oxide because this one is your giant ionic lattice structure. Same like KBr earlier. So between a metal and a non-metal. So not A, not D. We're looking at diamond, obviously, because in diamond, you're going to have each carbon bonded to 4 other carbon. But then diamond is an element, whereas SiO2 is a compound consisting of 2 or more different elements bonded together there. Graphite has a layered structure, even though it is giant covalent structure, but it doesn't have this kind of tetrahedral framework in 3-dimensional, unlike silicon 4 oxide there. Next one, which formula represent caffeine? So we're looking at the molecular formula, definition of molecular formula, total or the actual number of atoms. So the actual number of atoms in one single molecule. So what we're going to do is we're going to count the number of carbon. If you look at all of these, the only difference is 7 carbon versus 8 carbon. So if I count this 1, 2, 3, 4, 5, 6, 7, 8. So 7 there, this A is definitely wrong. Now let's count the hydrogen. I think oxygen is probably easier to count, but the oxygen is O2, O2, O2. No need to count the oxygen. Nitrogen is probably the next one I will count. If I see here N3, N4, N4, I can see 1 nitrogen, 2 nitrogen, 3 nitrogen, 4 nitrogen, which means that 3 nitrogen must be wrong. Now between the two molecules, C and D, only the 10 hydrogen and 11 hydrogens is the difference. So we have got 3 hydrogen there, another 3 hydrogen, 1 hydrogen, 3 hydrogen. So altogether is 3 plus 3 plus 3 plus 1. So that is 10 hydrogen there, meaning to say C must be our correct answer there. So question number 9, this looks like a mole calculation question. So we have been given reacting mass. So this is a concept called reacting mass. And we have to relate to these equations where this is saying 1 mole of zinc reacted with 2 mole of HCl. According to the equation, 2 mole of HCl, 1 mole of zinc, 1 mole of ZnCl2, and then 1 mole of H2. We're supposed to work out volume of hydrogen gas. So this is what we want to find. So I just put a question mark there. We have been given zinc information. We have been given HCl information. So this is about solution chemistry, where we have to think about N equal to C times V. C is the concentration of the solution in mole per dm cube. That makes the volume of the solution. That must be in dm cube as well in order for the unit to cancel out. As for the reacting mass, mole equal to mass over mR. The mass there must be in gram, and the unit of molar mass is gram per mole. How many gram in 1 mole? The thing about this question is they give you these two information, but we need to work out which one is limiting. That is the danger about this question. So we'll work out the mole of zinc, which is the mass over the mR. So 4.55 divided by 65 from the periodic table as the relative atomic mass. I get 0.07 mole. And then if I work out the mole of the HCl, which is C times V, so that's 2.25 mole per dm cube times 50 over 1000. That's the same as times 50 times 10 to the minus 3. And I get 0.1125 mole. So from the balance equations, you can see that 1 mole reacting with 2 mole. So if I have 0.07 mole, so this means that I need 2 times the mole of zinc, which is 2 times 0.07, so that's 0.14 mole of HCl is needed. But I only put in 0.1125 mole of HCl, so this means that you need this much, but you only have this much, so therefore what we put in is not enough. What we put in is not enough, therefore we can say HCl is limiting the reaction. HCl is going to be used up completely. So in terms of your molar ratio, so the mole of H2 is going to be related to the mole of HCl and not the mole of zinc there. So I'm running out of space here, but let me just use up the space on the left hand side further down there. So we can see that in terms of HCl is to the H2, 2 mole is to 1 mole of H2 there. So we said that the HCl is completely used up. So if that is 0.01125 is to X there. So we can see that when we do a cross multiply, 2 multiplied by that, so 2 times 0.1125 is equal to the other side, where I'm going to use pink color. So that's X times 1. So X being the mole of your HCl, so there's 0.225, sorry, I mean the mole of H2. I think I messed up my calculation there, beg your pardon. So what I mean is I would have this much mole of HCl, so 0.1125. Should really be careful with our mole calculation, shouldn't we? So there's 2x there. So 2x equal to 0.1125. So x is the mole of H2 there. This is the mole of H2, and therefore this is mole of H2 equal to the volume of H2. These are all the answers, A, B, C, D. These are all in dm cubed. So I'm going to divide that by 24 dm cubed per mole there. So moving up the 24 to the other side. So 0.1125 divided by 2 times 24. Should be able to just press my calculator, and I get 1.35 dm cubed there. The essence of this question, which one is limiting? Limiting versus excess is a very important concept. How much product you get comes from whichever one is completely used up, and there will be the HCl that completely used up as limiting. Then the mole ratio between HCl and H2, that's probably the more difficult bit in this particular question here. In this question number 10, so oxidation is occurring at electrode number 1. This is electrolysis, so we know about red cat. Red cat means reduction happens at cathode. That is because your cations are going to go to the cathode, and this makes cathode the negative electrode there. So if oxidation is happening at electrode 1 and reduction at electrode 2, so this must be negative electrode because it attracts the positive ions. So cations, which are positive ions, they go to the oppositely charged electrode, which is the cathode. Now, what is the direction of movement of electrons in the external circuit? Stated in the syllabus, these are in the metallic wires. So in the wires, the electrons are going to be moving towards the positive terminal. So this makes this one the plus and this one the minus. So we can think about electrons going that way because electrons want to go towards the positive part of the battery, and then they will go back that way. And having said that, this now makes sense because electrons are coming towards the cathode. You're going to do reduction, which is gaining electrons at the cathode, and you lose electrons from the anode. Well, oxidations, there's the loss of electrons from the anode. So in terms of the movement of electrons in the external circuit, it has to go from electrode 1 towards electrode 2. So 1 to 2 there, not 2 to 1. But in terms of positive ions in the electrolyte, the positive ions are going to be moving towards the electrode, which is negatively charged. So it's going to move towards the electrode 2, towards electrode 2. So this makes A as the best possible answer there. Question 11, when you have acid added to alkali, this is the H plus from the acid. This is the ionic equation that give you the neutralization bit. And this is the alkali, which is basically a soluble base. This base is soluble, giving you hydroxide solution, pH greater than 14, pH greater than 7. And then you have pH lesser than 7 for the acid. And you're going to get this ionic equation forming water, which is just pH 7. This is a classic reaction called neutralization. Neutralization is exothermic because when you think about the bond that you are forming and you're not breaking any bond at all. So for instance, that is your OH, and then you are just forming the new bond between the H plus and the OH minus. This is the new bond form. So forming new bonds is exothermic, and you are not breaking any old bond at all. You don't break the covalent bond here. You're just forming the covalent bond between the O and the H there. So this is neutralization. This is exothermic, just forming bond, which is exothermic reaction there. Question 12, we have information on 4 fuels. Which one is a gas at room temperature? This is 25 degrees Celsius. So looking at the melting point and boiling point, we want it to boil. So, already boils at 25 degrees Celsius. So therefore, the boiling point is below 25 degrees Celsius. So this means C and D must be wrong because you haven't boiled yet. So how can you be a gas at room temperature? The second one, this is about making 2 products when you burn in a plentiful supply of air. So this is in excess oxygen. When you burn in excess oxygen, this is your complete combustion, and complete combustion of this hydrocarbon fuel, not this hydrogen, because if you just burn hydrogen plus oxygen will just give you water as part of the fuel cell topic. This is a clean energy as you only produce water and not producing 2 products there. So B must be the only correct answer. When you burn that, the carbon is going to form carbon dioxide. The hydrogen there is going to form water. So that will be your CO2 gas and H2O liquid water when you combust the CH4 completely in excess oxygen. Question 13, we are given some bond energy here, and they are showing us how many bonds are broken and formed. So be very careful about counting this, especially for the CO2 and the H2O here. We are forming 4 times carbon oxygen bond, and we are forming 4 times OH bond there. So if I put in the value 4 times, what are we looking for? We are looking for this specifically, so this is 4 times X. If I say this is what we want to find, let this be X. And we can see from the equation above, I'm just going to do 4 times the bond energy for the OH, and we can combine them together as we are adding up the bond energy that you are forming. 4 times 4, 63, there's 1852 there. And then onto the reactant side, what are we breaking? We are breaking 1 time CC double covalent bond. There's your CC double covalent bond. 4 times CH, and 3 times OO covalent bond double there. So 3 times 4, 9, 6, and I have 4 times 412, and I have 1 times CC double bond, which is 612 there. Adding those up, and I get 3748 kilojoule per mole. So in terms of the bond energy calculation, we know the enthalpy change is the total energy for bond breaking minus the total energy for bond forming. So if you just sum up one section and then you take away the difference, bond breaking minus bond forming, 3748 minus 4x plus 1852, because there's algebra there. And it's supposed to give us minus 1408 kilojoule per mole according to the question there. So your job is to find out 4x. So 4x equal to 3748 minus 1852 plus 1408. So I move these to the other side, and I move the minus 4x to this side, and I open expanding the bracket there. There's minus 1852 there. So a little bit of algebra there. 3748 minus 1852 plus 1408. So 4x equal to 3304. So x equal to 3304, dividing that by 4. And I get 826 kilojoule per mole. And that is going to be option C there. Question 14, we have the student who added excess zinc. So excess zinc means that the HCl is limiting. If the HCl is limiting, the HCl is being used up. This is at 25 degrees Celsius. If you want to repeat the reaction at 50 degrees Celsius, this is higher temperature. So there will be faster rate. But then all other conditions remain the same. So that means in terms of your concentration, in terms of your volume, HCl is the same. So, but there will be the same mole of your limiting reactant, which is HCl limiting reactant. So that means it affects how fast, the temperature affects how fast, but not how much. So therefore, it's still the same volume of your hydrogen gas product. So there will be no change there. And what do we know? X is the original one. So X is our original one there. So meaning to say I can cross out D, I can cross out A, simply because these volumes are different. So between B and C, we can think about, the initial rate, that is looking at the gradient there. So this is the gradient of B. Then if I have another color there, this is the gradient at t equal to 0 initial rate. So we can see that this one is steeper gradient. So steeper gradient there would mean that in the same amount of time, going to produce more gas compared to the blue color one. So therefore, that will give you a faster rate of reaction. And that must be B we're looking for, faster rate of reaction there. Question 15, this is about reversible changes. The forward reaction is endothermic, so that means it absorbs heat energy from the surrounding. So this is going to be how we usually explain, equilibrium positions when temperature changes. You want to get highest equilibrium yield of NO2. NO2 is on the right hand side, so you want to favor right hand side. You want to get yield of NO2 increasing. So since your forward reaction is endothermic, as temperature increase, that means the equilibrium will try to decrease the temperature, as that is what equilibrium tries to do, to oppose the change, and it only knows how to absorb heat. So if I try to decrease temperature, I will absorb more heat from the surroundings. And looking at your first explanation, the forward reaction is endothermic. If I absorb more heat from the surrounding, therefore I will favor the forward reaction, because the forward reaction is endothermic, absorbing heat from the surrounding. Therefore I get more NO2 there. So we do want high temperature, not low temperature there. In terms of pressure, we need to count the moles of gases on the left as well as on the right hand side. 1 mole of gas on the left, 2 moles of gas on the right. So this is pressure versus equilibrium. So we count the moles of gas. There's 1 mole of gas on the left hand side versus 2 moles of gas on the right hand side. And that means the right hand side is going to exert greater pressure. So you want to favor the right hand side. You want to favor the side with more gases. Therefore, you should lower your pressure. So therefore, equilibrium will try to increase your pressure. How will equilibrium try to increase pressure? You will try to shift to the side with more gaseous molecules, which according to our first statement, that will be the right hand side, because the right hand side had 2 mole of gases. So the right hand side had more gaseous molecules, and therefore we do want low pressure here and not high pressure. So 2 is going to be what we're looking for if we want to favor the right hand side and get higher equilibrium yield of NO2 there. Question 16, this is about magnesium reacting with zinc oxide. So this is magnesium in 0 oxidation number as an element. And then you have the oxide of zinc, where we have O2 minus, so there's oxygen minus 2 oxidation number. Compound has no charge, so there's 0 oxidation number for zinc oxide. So zinc plus 1 times minus 2, zinc is plus 2. Can also think about the ionic compound, zinc 2 plus O2 minus. So this makes the zinc not 0, but plus 2 oxidation number there. Magnesium oxide, similar story. O2 minus Mg2 plus, so that's Mg plus 2. Oxidation number of an ion is the charge of the ion, and then zinc as an element, that's just going to be zinc 0 there. So looking at the changes in oxidation number, Mg0 to Mg2 plus, that is an increase in oxidation number. That's called oxidation process there. And the other side there, this is zinc 2 plus going to zinc 0. That is your reduction there. The zinc 2 plus has been reduced, where the oxidation number of the zinc has gone down. Which substance get oxidized? The oxidation number increased. That's going to be the magnesium, because magnesium oxide is a product. Definitely not the product. Definitely not the product. So it could be zinc oxide, but zinc oxide has gotten oxidized, I think. No, zinc oxide has gotten reduced. So the zinc plus 2 in ZnO going to Zn0 in zinc. And that is reduction there and not oxidation there. Question 17, we had an experiment. So a small volume of P was poured onto solid cube, the tap closed. Which one would cause the syringe to fill with gas? So which reaction would produce gas? Which reaction produce gas? HNO3 and Mg. So Mg is above hydrogen in the reactivity series. So that means magnesium is a reactive metal with nitric acid with any acid. So D must be wrong there. And then HCl with copper, about reactivity series. So copper is below hydrogen in the series, in the reactivity series. So that means that copper will not react with dilute acid there. No reaction with dilute acid, HCl. So having reaction there is wrong, which means I'm only left with C as the only possible answer. And we know sodium carbonate will definitely react with sulfuric acid. So C is definitely correct there. And they are looking for which one will react to produce gas, right? So if this one doesn't react, it doesn't produce the gas at all there. Not saying that it doesn't react with concentrated acid. It does with concentrated nitric acid. Very common reaction with copper. But there's concentrated acid, and the reactivity series is saying with dilute acid there. Question 18, ethanoic acid can react with water. So basically what happened is the CH3COOH will dissociate in water, and you will produce CH3COO minus plus H plus. So this is your partial ionization or partially dissociates in water in solution in order to give you your H plus there. So it donates a protons, not an electrons. So accepting a proton is going to be a base, not an acid. So really there's only one answer there, because what happened there is if I react this with water, then the H2O has got four other electrons. They are not used for bonding, and they can pick up a H plus, and that is essentially forming the H3O plus. So that can be imagined as H2O accepting H plus, whereas this thing donates the H plus there. Question 19. Aqueous ammonium sulfate. You react ammonia with dilute sulfuric acid. When you use ammonia as a base, you will not produce water. In order to balance the equation here, you will get a salt. The salt you get is what happened when you replace the H plus of acid with the another cations. The cations here is going to be ammonium cation. From the test for cations, we know about valency, which is the combining power of the ions. So plus 1 there, the combining power is 1. Minus 2 there, combining power is 2. So this second sentence, second line here, is about the exchange of the valency, the crisscross, and that give you 2. 2 of that NH4 plus. That will balance out the charges of this 1 SO4 2 minus. Its lowest common multiple, primary school mathematics. As such, the formula of ammonium sulfate, NH4 twice SO4. We write equation that we can balance. So there will be 2NH3. As you could see here, the 2 additional hydrogen come from the H plus of the acid, and you don't produce water, but this is neutralization. Acid plus base give you your salt neutralization there. This question is, how is solid ammonium sulfate obtained from this solution? The thing is, this is a solution, so it is soluble, but you want the solid, so definitely not filtration, as it is a soluble salt. It's going to be crystallization, and we know all ammonium salt, every salt that contain ammonium are soluble in water, and you have to obtain them by crystallization. Question 20. What property describe these two oxides? So CO2 is acidic, whereas CO is a neutral oxide. It's a factual question there. 21. Group 2 elements show the same trends as group 1 element. So group 1 element has one valence. Valence meaning outer shell, so one valence or one outer shell electrons, whereas group 2 has two valence or two outer shell electrons. But which one is the same trend as group 1 metal? Well, we're going to read through the options and think about what is exactly correct about group 2. The melting point is higher than the melting point of calcium. Well, we know about lithium, sodium, potassium. We know that down group 1, as part of the alkali metal series, we know that the melting point decreases, become easier to melt going down group 1 because of weaker metallic bonding. So now you have group 2 where you were told the trend is similar. So you have beryllium, magnesium, calcium, strontium, barium. So we expect the trend in melting point should be getting lower as well. That's the same factor, same trend as your group 1 metal. So melting point of barium is higher. That should be wrong, should be lower. In terms of reactivity, we think that reactivity of the metal increases down group 1, so it should increase down group 2 as well. So reactivity increases. Barium is more reactive than beryllium. B must be correct. Strontium will definitely react with oxygen, considering that strontium is going down in the group 2, so that's quite correct. So would not is wrong. Magnesium is more dense than barium, because that is wrong, as magnesium is less heavy compared to barium. Barium is further down, is much heavier than magnesium there. Question 23. What are the values for this? We just talked about the melting point going down group 1. So the melting point decreases as the metallic bonding getting weaker. Metallic bonding getting weaker because your size of the cations, so the radius of the cations increases down group 1 as you have more shells, and as a result the The charge is not as concentrated in the cations. In terms of density, density would increase because you have heavier mass, heavier AR. So in terms of the melting point, that should decrease, should get smaller and smaller. So X is smaller than 98. All of these are smaller than 98, but Y is going to be even smaller. So that thing is wrong there, as that is increasing. That is decreasing, that's okay. That's increasing, that's not okay. That's decreasing, that's okay. So A and C are all right. In terms of density, it should be higher than 0.97. So this is 0.26, which is lower than 0.97. So that thing is not okay for B. This is higher than 0.97. So that thing there, option D there, is going to be acceptable answer, not B. Question 23. We're looking at properties of transition elements. They do form color compounds. Think about iron 2 plus, iron 3 plus when they form different compounds there. Actually, by right, I should be talking about the different oxidation states in the next bit. So that is also okay. They have low densities, not okay. They do have high densities as they have very high masses. So very high relative atomic mass. Talking about color compounds, you think about, blue color CuSO4.5H2O when it's hydrated, and you have some other transition metal salts that are colored as well. Volatile means boils easily. That is not going to be true for transition metals, because what they are is they have giant metallic structure. Giant metallic lattice structure is part of structure and also bonding. This is the reason you have very strong metallic bonds, therefore very high melting point for transition metals there. So only 1 and 2 are correct. That's option A there. Question 24, this is the case study, extracting aluminium by electrolysis. We extract it from its ore, but the ore is not called cryolite. The ore is called bauxite. We are looking for correct statement. So aluminium is not formed at the positive electrodes because aluminium 3 plus is a cation. So the cation goes to cathode. Cathode is where positive ions get attracted to. Therefore, this is the negative electrode there. So we have bauxite. Bauxite is not used to lower the melting point. Bauxite is simply the ore. Instead, what you use is cryolite that you add together as part of the electrolyte to help decrease the melting point. And we do use graphite for both the positive and the negative electrodes. The negative electrode attracts cations. The positive electrode is anode because it attracts anions. But you have a side reaction which you produce oxygen at the anode, but you also have graphite anode as your electrode. What's going to happen then is your anode is going to weigh off as it forms this CO2 gas that will be formed at the anode, and therefore uses up and weighs off your anode in size. 25. Copper to nitrate and zinc carbonate. This is about heating strongly. This is a reaction called thermal decomposition. So the first thing we notice is that in terms of the nitrate, we don't just get nitrogen dioxide. If you write the balanced chemical equation, that's going to give you CuO, 2NO2, and you also get oxygen gas, which we need to balance. There are 6 oxygen atoms. There is 1, there is 4. I need 1 oxygen atoms. But to have 1 oxygen atom without changing the formula of the molecule, we get a half times 2, which gives you 1 oxygen atoms there, which is why we do get oxygen and nitrogen dioxide there, and not just nitrogen dioxide. In terms of the carbonate, so ZnCO3 decomposes to ZnO plus CO2. There is only CO2 gas being given off, not oxygen gas, and you can bubble the gas into lime water and it will turn milky or cloudy there. In this question 26, so iron from a blast furnace can be converted to steel. So we know that we have a high carbon steel, we will have mild steel as well. So this iron obtained from the blast furnace it contains roughly around 4%, not iron, but around 4% carbon. as far as I know. So some steel, such as mild steel only contains very little carbon, so that is only around 1% carbon. So that means that not all steel contains more carbon, so not always true, and therefore one cannot be correct there. So in terms of number 2, steel is produced by blowing oxygen through the iron. As far as we know, this is actually correct. So calcium oxide is added to molten iron to remove basic oxide. This is definitely wrong. You use it to remove acidic oxide. It's one of the steps to remove the SiO2 impurity. SiO2 silicon dioxide is acidic oxide. It will react with this calcium oxide, which is a basic oxide, in this neutralization reaction, where you will form a salt. This is between Ca2 plus and SiO3 2 minus. This is called silicate anion. Silicon just below carbon. Instead of carbonate, you get silicate anions, such that the charges of the ion cancel out and you just need one of each of the ions. This is called calcium silicate, or you just call it SLAC, and you can remove that acidic oxide using this basic oxide there. So 3 is definitely wrong there, leaving D as the only possible answer. Question 97, this is a factual question. To galvanize steel, we caught it with zinc, and zinc being more reactive than iron. So zinc being more reactive than iron, zinc is above iron in the reactivity series. So zinc will sacrifice itself instead of iron, and it will react with the oxygen in the air and corrode instead of the iron. Question 28, this is about purification of dirty water. So this is just passing through fine gravel and coarse gravel, and dirty water with the sand is going to get rid of the insoluble stuff. This is the filtration bit of the process there. I beg your pardon there. Question 29, which substance in polluted air damages stonework and kills tree? The idea here is damages stonework, so this has got to be from the acid rain component. Acid rain comes from acidic oxide. So between the carbon dioxide and the sulfur dioxide, carbon dioxide is weakly acidic, but it is not strong acid enough to, form acid rain and damages this stonework, such as the limestone building consisting of calcium carbonate kind of marble, and killing trees as a result of the acidic environment there. Question 30, this is about the Haber process to make ammonia. We know that N2 plus 3H2, reversible reaction to give it 2NH3. These are all in the gaseous state. This forward reaction is exothermic. We need a catalyst so that we could get a faster rate of reaction. It's got nothing to do with the yield, because catalyst does not affect how much, but only how fast the reaction is going on. So that means A and C must be out. As for high temperature, we know that high temperature can increase the rate, but it can also affect the equilibrium. But if we think about this forward reaction Haber process is exothermic. So that means that it releases heat energy to the surrounding, part of a case study. So when you increase temperature, high temperature, what will the equilibrium tries to do? The equilibrium, which is the system, will try to oppose the change. It will try to decrease the temperature, but you only know how to release heat energy. So in terms of releasing heat energy, we are going to release lesser heat to the surrounding, because we wanted the temperature to go down. So we will release lesser heat to the surroundings. And if we release lesser heat to the surroundings, based on the forward reaction from left to right releasing heat energy, so therefore we will release less heat to the surrounding. That means we will favor backward reaction. That means that you are going to get lesser of the ammonia. So that doesn't increase the yield. Increasing temperature will decreases the yield of ammonia. So that is wrong. But it does increase the rate of reactions in terms of collision frequency. That will increase. And also your particles will have gained more kinetic energy and colliding more frequently there. Question 31. We have this conversion of sulfur to sulfuric acid. This is part of this process, another case study in equilibrium and reversible changes. In the first stage, sulfur burns in oxygen. Well, it burns in air, which contains 21% oxygen as part of dry air composition, in which part is a catalyst used. We use it in the reversible step, which is this SO2 plus O2, giving us SO3. We're going to balance the equation with 2SO2, 2SO3. These are all gaseous reactant and gaseous product. This forward reaction is exothermic, but of course it being reversible, you do need all you can, all the specific conditions. There will be your 1 atm pressure, 1 to 2 atm pressure, not so high like Haber process, but you do need this high enough temperature to have fast enough of a rate while not compromising very low yield of the product, because the forward reaction is exothermic. But you also have the third condition. This is V2O5 catalyst to try and increase the rate of reaction. Naming the catalyst require the oxidation number of the vanadium. There's vanadium 5 plus, O2 minus, based on the valency, the charges of the ions. When you exchange the valency, that is your lowest common multiple, and that is going to give you 2 of that vanadium 5 plus and 5 of that O2 minus, like that, such that the formulation is V2O5 there. That is actually going to be stage B there, that actually uses the V2O5. We don't go sulfur trioxide to concentrated sulfuric acid. We don't do that directly because they'll be very dangerous in a factory setting, as they would create a lot of corrosive fumes. Instead, you produce this oleum, which is basically SO3 plus concentrated sulfuric acid. Then you add up all the atoms, H2, S2, or 7, which you can dissolve in water, and you're going to get 2 times H2SO4 to balance the equation there. Question 32, we use what as food preservative. It has an oxide, so there's SO2. That is your classic antioxidant in alcoholic drinks, in preserved fruits like dried peaches or dried fruits. They usually have SO2 as permitted antioxidant that will preserve your food and make them last longer. Which substance give off carbon dioxide heating? We're looking not at lime water. This is a solution. We're looking at limestone, which is calcium carbonate. And when you heat it, this is your thermal decomposition, giving you your group 2 oxide as well as this CO2 gas. This type of reaction is endothermic because you definitely need heating. So therefore, the reactants have to absorb energy from the surroundings, which you are giving it in the form of heat in order to decompose into the oxide and the carbon dioxide there. Question 34, very straightforward question, which I represent ethanol. This is a 2-carbon alcohol. Looking at the formula there, that is your CnH2n plus 2, because the molecular formula C2H6. This is your ethane. There's option A, definitely not ethanol. If we look at option B here, this is C2H4, CnH2n. This is a classic carbon-carbon double bond. There's your alkene there, definitely not your alcohol again. We can see our answer in C. There's your CnH2n plus 1 OH, C2H5OH there, and D there, that is your classic carboxylic acid family COOH like this. And then you have your CH3 there, so that is your ethanoic acid, because there's your 2-carbon carboxylic acid there. Question 35, we're looking at structural isomers. We want something which is correct. Same structure, different reactivity. No, maybe. Well, let's see. Let's go through the other option first. They have the same general formula, but different number of carbon atoms. Different number of carbon atoms is definitely wrong because they have the same molecular formula. So this is the actual number of atoms in one single molecule as part of year 9 definition. B is definitely wrong there. Different relative molecular mass will be wrong as well. Same molecular formula for that same definition. Different structures but same numbers of each type of atoms. That is going to be correct because same molecular formula. Different structural formula. So they're going to have different structure there. So this is a slightly differently worded kind of definition. Not necessarily different reactivity, because you could have a straight chain alkane versus a branch chain alkane. So different reactivity is going to be debatable depending on what we're looking at there. 36, what is the same in methanol, ethanol, and propanol? If I draw methanol, that is your CH3OH. If I draw ethanol, 2-carbon alcohol, so it's got the OH there, I don't necessarily have to draw them out. I mean, I can write the general formula. So the next one, I don't want to draw it out anymore. I would have 3 carbon, 1, 2, 3. So all of them will have the same CnH2n plus 1 OH. This is called the general formula, where I could sub in, N equal to 3 for 3 carbon, and then N equal to 2 for 2 carbon, and last but not least, N equal to 1 for 1 carbon. The general formula must be the same, as these are all alcohols family. You can see from the all part of the name there. That is 7. Ethene reacts with water under suitable conditions. Of course, that is when water exists as a gas. That is your case study of steam plus ethene, and that is going to give you your industrial process of making alcohol. That's going to be CH3, CH2OH. That is your ethanol from industrial process of adding steam onto alkenes. And this thing here is very, very particular. You're looking for which one is correct. The product has an MR of 46. So we look at the MR of C2H5OH. So that's 12 times 2 plus 5 plus 16 plus 1. So that is indeed 46. So we already gotten that. This is an addition reaction between the alkenes and the steam there. And you produce 2 different products. That is wrong, because this is an addition reaction. You only produce 1 product there. It occurs when ethene gas is bubbled into cold water. That is wrong. This is done at 300 degrees Celsius. Therefore, it's H2O gas. Therefore, it is steam there. And you do use a acid catalyst. That's your concentrated phosphoric acid, or we'll call it with the correct oxidation number, phosphoric 5 acid. The reaction is a redox reaction? No, it's not. It's an addition reaction. It's not a redox reaction there. Question 38, what do we have here? Ethanoic acid is made by reacting ethanol with this oxidizing agent. So oxidizing agent oxidizes the alcohol. So what type of reaction occurs? It's an oxidation reaction, where you can imagine that the carbon with the OH, that is this carbon here, the carbon with the OH would have lost the hydrogen, and loss of hydrogen is basically your oxidation in the context of organic chemistry. So oxidation refers to gaining oxygen atoms or losing hydrogen atoms there. Now you can see I have lost these 2 hydrogens and I've gained an oxygen. This is an oxidation reaction. Of course, oxidation of the alcohol would also mean the oxidizing agent get reduced. So you have KMnO4 minus. This will go from purple color, manganese plus 7. That's why you have the manganese VII that goes to manganese plus 2. That is your manganese 2 plus aqueous, as stated in your practical studies, which you will have seen this practical before if you did the actual practical in school. Question 39, we're looking at Terylene. I do believe that the new type of questions, they call it the PET. Doesn't matter what they call it, it is still a polyester. A polyester is going to consist of C double bond or like that. So that is your ester linkage. Do not forget that in the ester linkage, this is the bond that we form, and therefore this is the bond that we break if we want to identify that this bit is from the carboxylic acid end that contain the CO2H, and then the other side without the CO2H is from the alcohol having lost the H, whereas the carboxylic acid will have lost the OH as a result. Okay. So looking at these, we can see that this is amide. So this is what you call amide. And then this one is your starch. And then here we could see our ester linkages. I'm feeling that C is our answer, because D again, this is amide linkages. So C is polyester, and there's Terylene there. Question 40, so we are forming something called Kevlar. Looking at Kevlar, we can see that this is our amide linkages, as mentioned in the previous question. This is amide. If we break this bond that we have formed there, so we have lost the OH from the carboxylic acid, and we would have lost the H from the amine bit there. So what happened then is this must be condensation and not addition, because they involve 2 different functional groups. it's not just like alkene adding alkene together. We could see that we have a dicarboxylic acid, and we also have something called the diamine functional group, not diol because it's not forming ester, and this is dicarboxylic acid, 2 carboxylic acid on both end there, and we get a polyamide, not a polyester, because we have CONH and not C double bond OO. Like the previous question, there was polyester. This is a question of polyamide, C double bond O and H there. I do believe that that's the end of this October-November 2022 paper 2-1 extended for the Cambridge International IGCSE Chemistry. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. There's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. And do let friends know about the channel and the great videos that contain within. All the topical playlists are free, but do sign up and support my work through memberships to enjoy access to full paper tutorials that get updated from time to time, especially one new full tutorial video a week. Thank you for watching again. See you in the next tutorial video.